perfect.
Perfect.
Okay. If we were meeting in person, I would say, well, we'll take a break for a couple of minutes so people can stand up and walk around. But of course, on Zoom, you can stand up and walk around and no one will know. So it works out, it's easy. So that's just 1 second. So how do you pronounce your name? Jacob or Jakub or?
Jakub, but I'm fine with anything. Jacob, James, whatever.
Jakub Konieczny?
That is indeed the case.
Excellent. Okay, so our next speaker is Jakub Konieczny, who will talk about automatic semigroups. So please.
Thank you so much for this introduction. Your Polish is excellent. I will be talking about some classification problems for automatic semigroups and some related objects. All of this will be based on joint work with Oleksiy Klurman and also perhaps some results that came up in discussions with Adamczewski and Byszewski. So I'm going to assume that everybody knows what's a semigroup, but automatic sequences are a bit of a more exotic object. So let me start by a very brief introduction. Perhaps the most famous example of an automatic sequence is the 2-Morse sequence, which was actually discovered by Prouet. So it's a 0-1 valued sequence that has a couple of initial terms like so. And there's a bunch of different ways that you can think about this sequence. First of all, you can think about just an explicit formula. T of n is 0 or 1, depending on the parity of the binary sum of the sum of binary digits of n. Sometimes those numbers are called evil and odious. Now, you can think of this sequence as being produced by a finite automaton. Here's an automaton. I'm going to preferably define those on the next slide, but maybe you can already guess how it's supposed to work. You can define it by a simple recurrence relation, the one that's written over there. You can think of it as the fixed point of a substitution. So you start with 0 and you keep applying those rules, and in the limit you get the 2-Morse sequence. And you can also think about it from the point of view of algebra. Namely, if you construct a corresponding formal power series over F2, then it turns out that this formal power series satisfies some nice algebraic relation. And all of those points, except for the first one, are special cases of general characterization of automatic sequences. Now, let me define some of those terms properly. Let's start with automaton. So I'm going to need a little bit of notation. By sigma k, I'm going to denote digits base k. K is always going to denote a basis, so 10, 2, or whatever else you like. Sigma k star is strings of digits. And for an integer n by n in brackets, I'm going to denote the base case expansion. And conversely, for a string of digits w, I'm going to denote by w in brackets the integer that w encodes. Now, an automaton consists of the following data. First of all, we have a number of states, which are denoted by vertices in the picture on the right. One of them is distinguished as the initial vertex. There is a transition function, which takes a state and a digit and tells you which state to go to next. And we have an output function, which assigns to each state some value tau. Now, in order to use this to produce a sequence, we first extend the transition map to accept strings of digits by the rule that if you start at a state S and you read u v, then first follow the path encoded by u, and then follow the path encoded by v. And to compute the sequence, you start at the state as not the initial state. You write down the base case expansion of your integer. You follow the corresponding path, and at the terminal state, you read off the output function. So, for instance, this automaton over here produces the Rudin-Shapiro sequence, which is plus or minus 1, depending on the parity of the number of pairs of consecutive ones in the binary expansion of n. The definition itself is not particularly important. What you should remember is that automatic sequences are sequences that are somehow computable by a finite device. Another point of view has to do with kernels. So the k-kernel of a function of a sequence f consists of all possible restrictions of f to a residue class modulo a power of k. So for instance, for the 2-Morse sequence, the kernel consists of the sequence itself and one minus the sequence, so kind of the reversed sequence. For Rudin Shapiro sequence, we have a couple of nice recursive relations, and from them it's not hard to infer that the kernel consists of the Rudin Shapiro sequence and the Rudin Shapiro sequence restricted to odd integers. And as it turns out, a sequence is atomatic even only if it has a finite kernel. Now, a very natural class of problems for atomatic sequences is classification problems. So in the first instance, you can have a specified sequence A, and you would be interested if this sequence happens to be k-atomatic. More generally, you can think that you have a class of sequences, C, and you want to classify all the sequences in this class which are k-atomatic. A related notion is that of a k-atomatic set. So a set is atomatic even only if its indicator function is atomatic. So we're just working with 0, 1 valued atomatic sequences, nothing new happening here. And we can ask about a similar question where we have a class of sets S, and we want to classify all sets in this class which are atomatic. Now, some quick examples. Perhaps the most famous one is Cobham's theorem, which asserts that k-atomatic sequences which are also L-atomatic for some multiplicatively independent L are exactly the eventually periodic sequences. There's a number of very standard results about proving that sequences are not atomatic. For instance, one of the first things you learn about atomatic sequences is that the indicator functions of primes and the squares are not atomatic, and generally indicator function of the values of a polynomial of degree of greater than 2 are not atomatic. Another example that I personally find quite interesting is Alushan Shalit at some point classified all sequences of the form integer part of alpha n plus beta mod q, which are atomatic. Turns out these are exactly the eventual periodic ones. And together with Wyszewski, we extended that to all expressions that you can build out using polynomials and integer parts. Now, I'm going to talk about a classification of multiplicative atomatic sequences and multiplicative semigroups. So let me say a couple of words about what we would expect for this type of problem. Well, in additive combinatorics, there is a general heuristic that, well, the integers have an additive structure and a multiplicative structure, but those structures should not interfere with each other too much. For instance, we have the sum product phenomenon, where you can think about finite sets of integers. You can construct their sum sets and product sets, which are just what it says on the tin. And each of those two sets separately can be about as large as A. But if one of them is small, then the other one has to be large. So it has to be at least as large as A to 1 plus a constant. The best known constant is a third, and it is widely conjectured that one can take anything less than 1. Another related conjecture is due to Chaula. So it involves the Liouville function, which is -1 to the number of prime divisors. And it is, so this is very much a multiplicative object. Now, if you do something additive with it, namely take a bunch of shifts, multiply them together, and average, which is something very additive to do, you expect that you should see some cancellation, meaning that those k tuples should be uniformly distributed in plus -1 to the k. Now, there have been some very magnificent results along these lines by several different authors, Matomaki, Radziwiłł, Tao, Teravainen, and several others. But the question itself remains open. Now, what does it mean in our particular context? So multiplicative sequences and multiplicative semigroups are multiplicative, kind of tautologically. Atomatic sequences have more of an additive flavor. So heuristically, we would hope that there should only be certain trivial examples, and above that, nothing interesting should be happening. So here's a couple of examples of multiplicative sequences that are atomatic. So first of all, we have Dirichlet character and periodic sequences. We have sequences that only depend on the p-adic valuation. These are p-atomatic. And we have sequences that are eventually 0. Next, we have a couple of examples of multiplicative semigroups. So we have periodic semigroups. We have semigroups that depend only on periodic valuation. We have sort of a spurious example that if you take integers and you remove all the powers of p, then this is a semigroup and it is p-atomatic. And we have an annoyingly large class of examples where you can take any atomatic set whatsoever, multiply that by some integer m. This should be a union, sorry, and add to this all integers divisible by m squared, and this somehow trivially is both atomatic and a multiplicative semigroup. Now, let me say a couple of words about classification of multiplicative atomatic sequences. So first of all, to demystify the result slightly, let me mention that any multiplicative sequence whatsoever for each prime can be decomposed as the product of two terms. The first of them depends only on the periodic valuation. The second one of them depends only on the part of the integer that's not divisible by p. And this the part that's the second part is automatically multiplicative, and such a representation is unique. And there have been quite a few papers on the subject, and finally, together with Lemańczyk and Mullner, we were able to show that a multiplicative sequence is k-atomatic if and only if, well, if k has at least two prime divisors, then the sequence needs to be eventually periodic. If k is a power of a prime p, then we need exactly that both of those functions h and g in the decomposition above have to be eventually periodic. And in this case, in fact, g must be either genuinely periodic or eventually zero. And this is an if and only if statement. Now, for applications to semigroups, I'm going to need a slightly more general version of the statement, which involves the concept of a zero group. Now, a zero group is simply a group to which somebody added a zero. And zero acts multiplicatively just in a trivial way. Anything times zero is zero. So for instance, if you take any field, then the multiplicative semigroup is a zero group. Or if you take the circle and add to it the zero, this is again a zero group. And exactly the same statement can be proved for multiplicative sequences taking values in zero groups. I'm not going to repeat it because it's exactly the same. Okay, now let me move on to the main subject of this talk, namely the semigroups. Now, any p-atomatic set for a prime p can be uniquely decomposed as a union of sets as the union of the elements that are not divisible by p, the ones that are divisible exactly by p, the ones that are divisible exactly by p squared, and so on and so on. And if our set is atomatic, then the sequence of sets E0, E1, E2 is eventually periodic. And our main result with Oleksiy is that is the following. So suppose we have a set E, which is a k-atomatic semigroup. We will further assume that E contains an infinite pairwise co-prime subset. Now, if k has at least two parameters, then the set E has a very rigid form. It is a genuinely periodic set minus a finite union of geometric progressions, and those geometric progressions have ratios which are powers of k. If k is a power of a prime, then exactly the same statement holds for each of those sets in the decomposition corresponding to periodic valuation. Now, this is not quite an if and only if statement, but the reverse is not very hard to come by. And note that we need to assume this condition of having a finite, an infinite pairwise co-prime subset, because otherwise we run into those examples that I mentioned on the previous slide. Next, we have a very similar result, but now with an asymmetric version. I'm going to need a little bit of a notation. So for a set E and an integer m by E divided by m, I mean the set of all integers that when you multiply them by m, you land in E. I'm going to say that two sets are essentially equal if they agree up to density 0. And I'm going to say that a set is essentially periodic if it's essentially equal to a periodic set. Now, in the asymmetric case, we instead of a semigroup, we have a pair of sets EF, such that F times E is contained in E. To make things non-trivial, we need to assume that F is at least somewhat large. So we want that it has positive density. And for technical reasons, we want that K is co-prime to each element of F. Then we get a very similar assumption conclusion as on the previous slide, but we need to replace E with E divided by M for a certain M in F. So for the set E divided by M, we conclude that it's essentially periodic if K has at least two prime divisors, or each of the sets in the decomposition corresponding to p-adic valuation is essentially periodic in the case where K is a power of a prime. So this means that E is not itself periodic, but it contains a large periodic part. Okay, so now let me move on to saying a couple of things about how those things are proved. We will need quite a few facts about densities of automatic sets. So let me start by recalling a very classical fact that automatic sets have a logarithmic density. They are not guaranteed to have standard asymptotic density, but logarithmic density exists. And we are going to also exploit a certain equidistribution statement, which is, I think, quite folklore, but we weren't able to really find it anywhere in the literature, so we just proved it from scratch, which asserts, roughly speaking, that there's some maximal period delta such that an automatic set can exhibit delta periodic behavior, but other than that, it's nicely distributed in residue classes. So in other words, we claim that there's an integer delta such that for each modulus q, for technical reasons, we need to q to be co-prime to k. If we want to compute the density of E restricted to a residue class modulo q, it's up to scaling the same as the density of E in the residue class modulo q prime, where q prime is the greatest common divisor of q and delta. So in particular, it's at most delta. A slightly more elegant way of stating this fact is that E minus C divided by Q has the same density as E minus C divided by Q prime, with Q prime as above. As a particular case, each automatic set is equidistributed in modulo class modulo each sufficiently big prime. Now the time is running, so I will skip an outline of this proof and let me move on to how we are going to use that theorem. So a crucial advantage that this theorem gives us is that we can use it to find invariance, multiplicative invariance of our set. So suppose that we have an automatic semigroup E, and that we can find some element Q of E that's co-prime to this constant delta from the previous slide. And then I claim that E divided by Q is essentially equal to E. Now, because E is a semigroup and Q is in E, we have E divided by Q is at least as large as E. On the other hand, because of the theorem, the densities agree. So, so from those two facts, we immediately conclude that the two sets are essentially equal. This motivates us to look at the set of integers of approximate multiplicative invariants of our set E, and at the set of reverse of elements which divide some of the elements of inf E. In fact, what we prove is that if we have an automatic set E and an automatic set F, which is contained in inf E and has positive density, then for more than 2 prime factors, the set E has to be essentially periodic. When the base is prime, we have that each of the sets in the decomposition is essentially periodic. Now, the reason why it's good to look at those sets in inf and ref is that they allow us to construct a multiplicative sequence which somehow encodes the multiplicative invariance of our set E. Namely, we show that there exists a zero group together with an epimorphism or a multiplicative sequence, if you will, such that inf E is exactly the pre-image of 1, ref E is exactly the pre-image of G. And in fact, this epimorphism is totally characterized by saying that 2 elements Q and Q prime in ref map to the same point if EQ divided by EQ prime are essentially equal. Now, let me try to say a couple of words about the proof. There's a quote by historian Pierre Briand that I really like. You must believe in ancient history even if it is not true. And I encourage you to think about this proof in the same spirit. So we are in the following situation. We have a pair of automatic sets. EF is contained in inf E. It has and F has positive density, and we want to describe E. To simplify, we assume that K is the power of a prime, and this prime doesn't divide any element of E or F. First, we show that ref E is periodic, and this is fairly easy. Basically, the key idea is that for sufficiently large primes by the equidistribution theorem, F divided by P has the same density as F, so in particular it's positive. So in particular, F contains a multiple of P. So in particular, P is in ref. And once you have all the big primes, it's not hard to see that we have periodicity. The next step is to show that the group G is finite, I'm going to slightly cheat here, but the basic idea is again to use to notice that if it was infinite, that we could construct an infinite sequence Qi with all different images. Now, if those images are distinct, then it's not hard to see that inf E over Qi's have to be pairwise disjoint. But this means that F divided by Qi have to be pairwise disjoint. But all of those sets have density that's same as F. So we would have an infinite number of sets with density bounded away from 0, which would additive the fact that density is additive. Now, the part which is a bit too optimistic is that I want to say that pi is K automatic. Now, in reality, it's not. But why would we why would we think that it might be? Well, because G is finite, we could find a finite list Q1 up to QH such that the images of those elements cover all of the group G. Now, because ref is periodic, we can easily detect whether whether Q maps to 0 or not. So all that we really need to do is given an integer Q, about we know that it lands in ref, we need to find the value, and we know that there is a unique value such that E divided by Q is essentially equal to E divided by Qi. Now, if we knew that for Q and Q prime with the same image in the group, those sets E divided by Q and E divided by Q prime are exactly equal, then in order to verify this condition above, it would suffice to check that those two sets agree on a sufficiently long interval. And this is something that a finite automaton can do. Hopefully one might expect that the fact that its approximate equality shouldn't change too much. Now, imagining that we know that, we would conclude that pi is periodic, which follows almost directly from our characterization of multiplicative automatic sequences. And once we know that pi is periodic, it's merely a technicality to show that E is essentially periodic. It's not super easy, but it's more mundane than thought-provoking. So that would finish the argument. I think 30 seconds over time, so I'll just very briefly say that in reality, we need to introduce a new set of invariants for which is somehow related to that old one, and for which we really do have exact equality, so we're able to employ this argument. So in some moral sense, this argument is what we do, except there's a lot more technicalities in the background. And on this optimistic note, I'm going to finish the talk, and thank you so much for your attention.
Thank you, Jakub.